You are standing in a dark control room, listening to the soft hiss of old data crossing billions of miles. The subject is the heliopause, a thin and nearly invisible border at the far edge of the sun's reach. NASA now says that border is not sitting still, and if it is changing, our whole map of home changes with it. Subscribe for more stories that turn distant space signals into ideas you can actually picture and remember. Far beyond Mars, beyond Saturn, beyond the dim ring of small icy worlds, the solar system does not end with a sign. It fades into a strange shoreline made of particles, magnetic fields, and pressure that no human eye can see. For years, many people imagined that shoreline as a clean shell, a bubble with a clear inside and outside. That picture was neat, simple, and comforting. But space does not care what feels neat to us. At the edge of the solar system, the sun is not meeting empty blackness. It is meeting the thin gas between stars, and the meeting is messy, slow, and alive. The farther we have looked, the less that border has behaved like a border. 2 old spacecraft helped crack the first part of the mystery. One small mission the size of a bus tire helped widen it, and now a newer NASA mission is arriving with sharper eyes at exactly the moment this story gets stranger. What once looked like a wall now looks more like weather. That matters more than it sounds. This outer shield helps block dangerous cosmic rays, the fast particles that come from violent events across the galaxy. If the shield swells, wrinkles, leaks, or shifts, then the conditions around every planet inside it shift too. The story out there is quiet, but the consequences reach all the way back to us. So when NASA says something strange is happening at the edge of the solar system, it is not talking about a monster. It is talking about our protective bubble, the giant magnetic shell blown by the solar wind from the sun. And what NASA has confirmed is not one strange object, but a strange behavior. The edge is moving, changing shape, and refusing to stay simple. To see why this matters, we need to step back. Most people picture the edge of the solar system as a fixed line, like the skin of a soap bubble, where you cross once and you are simply outside. The real story begins with the sun doing something easy to miss. Every second, it throws out a stream of charged particles called the solar wind. That wind races away in all directions, past Earth, past the outer planets, and far beyond Pluto. As it spreads, it blows a huge bubble around the planets and most of the small bodies that orbit our star. That bubble is called the heliosphere. It is not made of glass, rock, or ice. It is made of motion, pressure, and magnetic force, which is why it is so hard to imagine. You cannot point a telescope at it and see a shining rim. If you want a simpler picture, think of walking fast through cold fog. The air in front of you pushes back, your coat gathers moisture, the space around you changes shape because you are moving through something, even if that something looks empty. The solar system does that too. Our sun and its bubble are moving through the local interstellar medium, the thin gas between stars. NASA scientists sometimes describe our nearby region as a cloud of hot material, often nicknamed the local fluff. That soft name hides a hard fact. We are not drifting through nothing. Where the outward push of the solar wind meets the inward pressure of interstellar space, things pile up. The solar wind slows at a region called the termination shock. Beyond that lies the heliosheath, a rough middle zone where hot solar particles and outside material mix. Farther still is the heliopause, the outer boundary where the sun's direct grip gives way. That sounds clean on paper. In schoolbook drawings, it often looks clean too. One bubble, one rim, one outside. A picture you can hold in your head in a few seconds. And for a long time, that was good enough. The edge was too far away to test directly. Even Pluto is close compared with the heliopause. Only a few spacecraft ever had a chance to travel into that region, and only 2 actually did. Those were Voyager 1 and Voyager 2. They launched in 1977, when many of today's viewers were not even born, and their parents may still have been kids. They flew past the giant planets, did the first close visits to Uranus and Neptune, and kept going. What began as a planetary tour slowly turned into an interstellar mission. There is something almost eerie about the Voyagers now. They are still talking, but faintly. Their signals take many hours to reach Earth. By the time a message arrives, the spacecraft is already somewhere else, still moving into deeper dark. Because of them, scientists could finally ask a real question instead of drawing another guess. What does the edge actually feel like? Does the magnetic field turn sharply? Does the particle mix change all at once? Does the outside begin with a clean step or a blurred one? Before Voyager 1 reached the boundary, many models gave a simple expectation. Charged particles from the sun should fall, cosmic rays from outside should rise, and the direction of the magnetic field should change sharply as the craft crossed from the sun's domain to interstellar space. That idea made sense. Inside the heliosphere, solar plasma carries the sun's magnetic field. Outside, interstellar plasma should carry a different field. So if Voyager crossed the heliopause, the field should seem to twist like a compass swung to a new north. It was a strong, tidy prediction. In 2012, Voyager 1 reached the region where that prediction should have paid off. The count of particles from inside the heliosphere dropped hard. Galactic cosmic rays jumped to their highest levels of the mission. On paper, it looked exactly like the great crossing everyone had been waiting for, but the magnetic field barely changed direction. In a 2013 Jet Propulsion Laboratory report, Voyager project scientist Ed Stone of Caltech said the change was less than 2 degrees. The strength of the field jumped, yes, but the direction mostly held. It was like opening a front door and finding the air outside different, while the wind still seemed to blow from the same street. That was the first reason the edge became strange. Voyager 1 seemed to be outside, but not outside in the clean way the textbooks had prepared people for. Stone said the team had to be cautious because this was one of exploration's great milestones. No one had been there before, and the guidebooks were incomplete. Another clue came from sound, if we can call it that. Voyager 1 carried a plasma wave instrument. It could not hear sound in the human sense, but it could detect vibrations in thin, charged gas. Those vibrations let scientists estimate how dense the surrounding plasma was. In April 2013, that instrument picked up plasma oscillations triggered by an earlier burst of solar activity. Don Gurnett and Bill Kurth at the University of Iowa studied the signal. The density came out far higher than the plasma inside the heliosphere. That was the signature of interstellar space. So Voyager 1 was not simply in the old solar bubble, it was bathing in matter from other stars, as Stone put it. Yet the sun still seemed to matter there. Even this first direct crossing suggested that the boundary was not a door with a clear hinge. It was more like surf. Voyager 2 made the setup even stronger. It crossed the heliopause on November 5, 2018, at a different place and at a different time in the solar cycle. That mattered because scientists expected the heliosphere to expand and contract a bit, almost like a lung. A moving bubble could explain different crossing distances without changing the basic picture. NASA's 2019 summary of 5 Nature astronomy papers said Voyager 2 confirmed several simple ideas. The plasma outside was denser than the plasma inside. The outside was colder than the inside. The crossing also produced the expected plunge in solar particles and a rise in cosmic rays. So the old picture still seemed alive. Yes, the edge might breathe in and out. Yes, the crossing might happen a little farther or a little closer depending on solar activity. But it was still easy to imagine one boundary and one main event. Cross it, and the story is done. That is where many people still mentally stop. They picture the edge as far away, invisible, and basically settled. A line that might wobble, but a line all the same. And that is exactly the assumption this story is about to break. But that picture is about to change. The farther NASA looked, the more that clean border behaved like a layered, shifting, partly leaky system instead of a fixed shell. What we have just taken for granted turns out to be a small part of a much larger story. Write the moment this idea cracked for you in the comments. That one detail helps us build the next story around the exact point where surprise turns into real understanding. The first real fracture in the old idea did not come from a dramatic image. It came from a mismatch. Scientists expected a sharp magnetic turn at the heliopause. Voyager 1 found a huge particle change, but almost no turn at all. That forced a harder thought. Maybe crossing the boundary was not the same as leaving all solar influence behind. Maybe the outside of the heliosphere was not a clean outside. Maybe the border was a mixed region, where old rules fade slowly instead of snapping off. Ed Stone said as much in 2013. Voyager 1, he explained, was in interstellar space, with disclaimers. That word matters. A disclaimer is what you add when reality is more complicated than the headline, and at the edge of the solar system, complexity kept piling up. Then, Voyager 2 arrived with a second sample. Scientists hoped the second crossing would clear up the first. If Voyager 1 had just hit an odd local patch, Voyager 2 might show the neat field turn everyone expected. Instead, it confirmed the strangeness. NASA reported in 2019 that the magnetic field just beyond Voyager 2's crossing was also nearly parallel to the field inside. What was expected was a visible bend. What was found was alignment. It was like stepping out of one river into another and finding both streams running almost side by side. Voyager 2 added another surprise. Scientists expected nearby interstellar plasma to be colder and denser than the plasma inside, and it was. But it was also a little warmer than expected. That hint suggested compression on the outer side of the boundary, while Voyager saw compression on the inner side too. Picture a mattress pressed from both directions. That was the feeling of the data. The heliopause was not just a skin, it seemed squeezed, active, and shaped by forces on both sides at once. Even now, NASA says the cause of that compression is not fully understood. Then came the leak. One Voyager instrument detected a trickle of particles from inside the heliosphere slipping through the boundary into interstellar space. What was expected was a stronger separation. What was found was porosity. Not a solid seawall, but a barrier with tiny paths through it. And location seemed to matter. Voyager 1 crossed closer to the front of the heliosphere, the direction the solar system is moving. Voyager 2 crossed nearer the flank, more to the side. NASA said that flank appeared more porous than Voyager 1's region. So even the leakiness of the border may change from place to place. By itself, that would already be strange enough. But another mission had been staring at the solar system's edge in a very different way. It never traveled there. It stayed much closer to home and mapped the boundary using fast neutral particles that came back from the edge. That mission was IBEX, the Interstellar Boundary Explorer. IBEX was small. David McComas of Princeton University once pointed out that it was about the size of a bus tire. But it did something huge. It watched energetic neutral atoms, tiny particles created when the solar wind smashes into interstellar material near the boundary, and some particles shoot back inward. That gave scientists a kind of echo map. Think of shouting into a canyon and timing the echo. IBEX did that with particles instead of sound. It collected only about one particle every other second, but over years those returns built a picture. And in 2009, that picture showed something nobody had predicted, a bright diagonal feature now called the IBEX Ribbon. What was expected was a rough glow around the boundary. What was found was a long, strong stripe. The surprise was not small. NASA's Eric Christian later called it a structure 1 billion miles wide and 10 billion miles long that no one knew was there. The edge had drawn a line across space like a hidden seam. For years, scientists argued over what could make the ribbon. The best clue was that it seemed tied to the direction of the interstellar magnetic field. That meant the shape and behavior of the edge were being guided not just by the sun, but also by conditions in the galaxy around us. The boundary was already sounding less like a wall and more like a negotiation. Then, nature ran an experiment for us. From about 2009 to 2014, the solar wind stayed fairly low and steady. According to Princeton's 2020 research release, the heliosphere contracted in those years. Then, in late 2014, NASA spacecraft near Earth saw solar wind pressure jump by about 50%. The sun had, in effect, given its outer bubble a shove. Scientists expected that shove to matter eventually. They did not know exactly how the edge would answer. 2 years later, IBEX saw the first sign. Energetic neutral atoms coming from near the heliosphere's nose grew stronger, telling researchers that the pressure pulse had reached the outer regions and sent a signal back. David McComas and colleagues tied that return signal to the 2014 solar wind increase. Their 2018 Astrophysical Journal Letters paper argued that a pressure wave moved outward, hit the far regions, and partly rebounded. What was expected was delay. What was found was a measurable echo. Like clapping in a dark house and realizing the hallway is longer than you thought. Eric Zernstein, then at Princeton, and Jacob Herrikheisen at the University of Alabama in Huntsville pushed the story further. In a 2018 Astrophysical Journal paper, they modeled how that pulse should spread. It did not just brighten one patch and stop. It should create an expanding ring across the sky as the signal reached more distant parts of the boundary. That was a huge shift in how to imagine the heliosphere. A fixed wall does not send back a growing ring over years. A living structure does. What was expected was a line. What was found was motion with memory, like ripples running across a pond long after a stone falls in. The model suggested that 3 years after the 2014 pressure increase, the termination shock could move outward by about 7 astronomical units. The heliopause could shift outward by about 2 astronomical units, and then about 2 more the next year. Those are giant numbers. 1 astronomical unit is the distance from Earth to the Sun. So yes, something strange was happening at the edge. The edge was being pushed outward by changes that began at the Sun years earlier. And because the response came back as particles, scientists could watch the bubble react with a long delay. The border did not just exist, it answered. In June 2020, NASA and Princeton summarized 11 years of IBEX data in the Astrophysical Journal supplements. McComas, Justina Sokol, and Jamie Salai describe the heliosphere almost like a breathing thing. When solar wind gusts rose, the heliosphere inflated. When the wind calmed, it contracted. The key detail was timing. The response at the edge lagged the changes at the Sun by roughly 2 to 3 years. What was expected was change, maybe. What was found was a clear echo with a clock built into it. Like seeing a flash far away and hearing the thunder much later, except the storm was our star. And the change was not even. The outer bubble did not swell in a perfectly balanced way. Princeton's release said the response was asymmetric, which means uneven from one side to another. That pushed scientists toward a picture more like a comet than a neat ball. The Sun sits closer to the front, with a longer tail trailing behind. Now we reach the part where even the experts step carefully. Not everyone agrees on the exact shape. Some models once favored a more globe-like form. Others famously suggested something closer to a croissant. That disagreement is not a weakness in the story. It is proof that the edge is complicated enough to resist easy geometry. But the broad point held. The heliosphere was not still. It was changing with the solar cycle, and it was changing unevenly. Time and those returning neutral particles, McComas said, were painting the distances and the shape for us. The map was becoming dynamic. Then another clue arrived from New Horizons, the spacecraft most people know for Pluto. Far beyond Pluto now, New Horizons carries an instrument called SWAP, short for solar wind around Pluto. In 2020, a study led by Pavel Svacina and published in the Astrophysical Journal used SWAP data to estimate the density of neutral hydrogen around our local interstellar neighborhood. The result was higher than several later studies had suggested. The number was about 0.127 particles per cubic centimeter, roughly 40% more hydrogen than some earlier estimates. What was expected was a thinner interstellar fog. What was found was a thicker one. Eric Christian of NASA compared it to running through mist and getting wetter than you thought you would. More outside material means more drag, more pickup ions, and a different edge response. That denser outside gas may help explain why the IBEX Ribbon looked brighter than some models predicted. In other words, part of the mystery at the edge may come from what the solar system is plowing through, not only from what the Sun is pushing out. The border is a meeting place. To understand it, you have to understand both sides of the meeting. Now the full reveal starts to settle in. Voyager showed that the crossing is transitional, compressed, and sometimes leaky. IBEX showed that the whole boundary expands and contracts over years and answers solar changes with delayed echoes. New Horizons showed that the local interstellar medium may be denser than we thought. Put those together, and the old picture falls apart. The edge of the solar system is not a fixed rim. It is a moving, uneven, partly porous shield that stores the memory of solar activity and reshapes itself as the Sun moves through the galaxy. That is the strange thing NASA has effectively confirmed. And here is the deepest twist. The strangest behavior may not be one event, but the fact that the edge acts like a system. It breathes, it wrinkles, it compresses, it reacts late and differently depending on where you look. So when a headline says something weird is happening at the edge of the solar system, the careful version is even better. Something weird has been happening there for years, and now we have enough missions, enough crossings, and enough echoes to stop calling it a fluke. We are watching our cosmic shield behave like living weather on a scale of billions of miles. That is not less dramatic than a single mystery object. It is more. Share this video with the one friend who still thinks space is just empty black distance. Passing the story to one skeptic helps turn a far-off fact into a human-sized idea that sticks. And here is where this stops being about one spacecraft and begins being about us. If the edge of the solar system is a changing shield instead of a fixed shell, then our place inside it is not passive. We live inside a system that is constantly adjusting the terms of our safety, our measurements, and our understanding. That shift matters for wonder, but it also matters for planning. A moving shield changes how cosmic rays enter the heliosphere, how we think about long missions, and how we understand the neighborhood our Sun is crossing. The story at the edge becomes, very quietly, a story about the future of life and travel closer to home. The next phase of this story is already underway. NASA's Interstellar Mapping and Acceleration Probe, or IMAP, launched on September 24, 2025. Its whole job is to map the heliosphere's boundary in much greater detail than IBEX could manage. Where IBEX sketched the outline, IMAP is meant to sharpen the map. NASA says IMAP carries 10 instruments. It sits near the Sun-Earth L1 point, about 1 million miles sunward from Earth. From there, it can watch incoming solar wind, while also collecting particles that carry news from the outer boundary. It is both a lookout tower and a cartographer. That mix is important. The same mission that helps study the far edge of the solar system can also improve warnings of hazardous space weather near Earth. NASA says IMAP can provide roughly a half-hour of warning for dangerous solar particles moving through near-Earth space. So the strange behavior at the outer edge is not sealed off from daily life. It connects to satellites, astronauts, and power systems here. If you want a domestic picture, think about weather reports before a storm. You check your phone. You bring in the patio chair. You charge what needs charging. Now stretch that idea into space, where the storm source is the sun, and the shield around the whole solar system changes over time. A better map of the heliosphere helps tell us how much galactic radiation gets filtered before it reaches the inner planets. That matters for astronauts heading beyond Earth's magnetic cocoon. It matters for spacecraft electronics. And it matters for any future in which crews spend months or years farther from home than any crew has gone before. There are still open questions, and they are big ones. How long is the heliotail, the trailing end behind the sun's direction of travel? How uneven is the flank compared with the nose? How much of the boundary's leakiness is local and how much is global? The answers are not small details. They change the whole shape of the shield. Scientists also want to know how exactly the IBEX ribbon is produced. The leading idea involves a secondary process in which particles cross the heliopause, lose and regain electrons, and return after a longer trip. That would explain why the ribbon responds later than the rest of the boundary. But the full picture is still being tested. The edge keeps offering clues, not final speeches. Meanwhile, the old scouts are still out there. NASA said on April 17, 2026, that engineers shut down one instrument on Voyager 1 to save power and keep the spacecraft operating longer. Voyager 1 still has 2 science instruments running. The mission page says both Voyagers were still functioning in April 2026, nearly 49 years after launch. Even now, the oldest witnesses are still whispering. That gives this story a strange emotional shape. The spacecraft are aging, their power is fading, but just as their voices grow weaker, newer missions are arriving with sharper tools. Exploration is handing the notebook forward line by line, from 1977 hardware to 2026 analysis. The numbers also keep getting more precise. The 2014 solar wind pressure jump was about 50%. The magnetic field change at Voyager 1's crossing was less than 2 degrees. The denser local hydrogen estimate from New Horizons was about 0.127 particles per cubic centimeter. These are not vague signs anymore. They are measurements building a case. And the dates matter too. Voyager 1's major crossing evidence centered on August 25, 2012. Voyager 2 crossed on November 5, 2018. IBEX's 11-year boundary study was published on June 10, 2020. IMAP reached its destination near L1 on January 10, 2026, and NASA says its 2-year primary science mission began on February 1, 2026. That growing precision tells you something beautiful. We are no longer only saying the edge is far away and weird, we are timing it. We are measuring how fast signals travel from the sun to the boundary and back. We are catching the heliosphere in the act of changing. What should you watch for next? Watch for IMAP maps that sharpen the asymmetry. Watch for better estimates of how far the heliotail extends. Watch for fresh work on whether the boundary behaves more like a smooth front, a rippled membrane, or a set of changing layers. And watch for every small update from the Voyagers, because each one may be among the last from the first machines that touched this frontier. There is also a larger lesson here. We often talk about the solar system as if it were a finished place, with named planets and settled edges. But the boundary of home is still being discovered, not because it moved while we were not looking, though it did, but because it is the kind of thing that only becomes real once you gather time, patience, and evidence. One day, if humans travel far enough, the heliopause may stop being an idea and become a route. Crews may study its shifts the way sailors once studied tides. Engineers may plan missions around the breathing of the heliosphere. And children who hear this story now may grow up thinking of the edge not as the end of the solar system, but as its living skin. What comes next will not arrive with fireworks. It will arrive as better maps, cleaner models, and tiny particles counted one by one. Somewhere, a researcher will notice a ring expand a little farther than expected, or a ribbon brighten on schedule, or a density value settle a long argument, and a quiet piece of the universe will become a little less hidden. That is how this frontier moves, not with a giant reveal all at once, but with a chain of patient confirmations. A signal leaves the sun. Years later, it reaches the far boundary. Years after that, the answer comes home. Soon, more of those answers will start arriving. IMAP is in position. Voyager is still reporting. The outer edge of the heliosphere is still reacting to conditions set in motion long ago, and the delay means tomorrow's discoveries may already be on their way. We are living inside a story whose ending travels slower than light headlines. So keep one image with you. Not a dramatic explosion, not a spaceship racing through flames. Just a thin, shifting border billions of miles away, breathing in slow motion as the sun presses outward and the galaxy presses back. That is the edge of our home. Save this story and come back when the next IMAP maps arrive. Keeping the timeline close will help you feel the future in real time instead of hearing about it after the fact. Because the future of this mystery is not whether the edge exists, it is how finely we will learn to read its changes. A ring here, a ribbon there, a density value, a field angle, a pressure wave with a date attached. The map is getting sharper, and when it sharpens enough, we may look back at the old idea of a clean solar system border the way we now look at old maps with blank oceans. Useful for their time, brave even, but missing the currents. Some night, years from now, another quiet packet of data will land in a control room on Earth. It may come from a fading Voyager system, or from IMAP's newer instruments, or from a mission not yet built. And inside that packet will be one more clue about the moving skin of the solar system. I think it will tell us what the best exploration stories always tell us. Home is larger, stranger, and more alive than we knew.